Welcome, medical students, and everyone joining us on the deep dive. Ever wondered about those, unseen architects of disease, these master strategists of survival lurking all around us? Well, today we're plunging right into the ingenious world of parasite groups. These are organisms that really push the boundaries of adaptation. We're basing this session on the brilliant notes from Dr. Mohammed Wiesman Abdul Hamid. He's a medical lecturer of the Medical Parasitology and Entomology Unit, Faculty of Medicine and Defense Health at the National Defense University of Malaysia in Kuala Lumpur. So by the end of this deep dive, you should have a really clear picture. You'll be able to name the major groups and subgroups, understand how we classify them. You'll recognize common examples, grasp their features, how they reproduce, and they're often quite cunning life cycles. Think of it as your guide to these, well, sometimes microscopic, sometimes not so microscopic marvels. Okay, let's unpack this fascinating world. So to really get a handle on parasites, where do we even begin? Like, in the grand scheme of things, the tree of life.
That's the perfect place to start, yeah. Imagine all life going back to one single ancestor. We call it LUCA, the last universal common ancestor. From LUCA, life branched out into three huge domains: bacteria, archaea, and eukaryota. And for our purposes today, eukaryota is the key domain. It's where all complex life evolved us: plants, fungi, animals, and crucially, every single parasite we'll be talking about. So they're all eukaryotes, sharing that ancient, more complex lineage.
That really helps set the stage.
Yeah.
But okay, what's the big deal about a cell's structure? Why is that basic blueprint, so critical for telling life forms apart, especially when we're trying to understand parasites?
Oh, it's absolutely fundamental. It's like knowing the difference between a basic tent and a complex building. The prokaryotic versus eukaryotic split dictates almost everything. So prokaryotic cells, like bacteria, they're simpler, no true nucleus. Their DNA is just sort of a circular chromosome floating in the cytoplasm in a region called the nucleoid. And they lack those internal membrane-bound compartments, the organelles like mitochondria or Golgi apparatus. They have a pretty basic setup. But eukaryotic cells, they're much more complex. They have a proper membrane-bound nucleus housing multiple linear chromosomes. They're generally larger, packed with all those specialized organelles doing specific jobs, much more organized, more efficient. And they divide using complex processes like mitosis or meiosis, not the simple binary fission you see in prokaryotes. This complexity matters because parasites are eukaryotes. They have these advanced features, which means they operate on a different level biologically compared to, say, bacteria.
Right, so they're eukaryotes, more complex. Where do they fit then within the bigger field of microbiology, alongside viruses, bacteria, fungi?
Good question. Microbiology is, well, huge. It covers all those microscopic things: viruses, bacteria, fungi. But when we focus specifically on parasites, we enter a subdiscipline called parasitology. And within medical parasitology, we break it down even further into three main areas. There's protozoology, the study of those single-celled protozoa, then helminthology, which deals with parasitic worms, and entomology, focusing on insects and other arthropods, which can be parasites themselves, or very importantly, act as vectors transmitting other parasites. So it's a specialized corner of microbiology.
Got it. Okay, now let's get into the nitty-gritty of classification. What's the very first, most basic way we divide parasites up, the fundamental starting point?
The absolute first cut is incredibly simple. It's based on the number of cells. We split them into unicellular and multicellular. Unicellular parasites are the protozoa. Just one single cell has to do everything: eat, move, reproduce, the ultimate multitasker.
Right.
Multicellular parasites are called metazoa. They're made of many cells, often specialized into tissues and organs. Much more complex structures, more complex life strategies. This single cell versus multi-cell difference is really the foundation.
And within those big buckets, unicellular and multicellular, what are the main groups we're really going to zoom in on today, the ones most relevant for, say, medical students?
Okay, so for the unicellular protozoa, we'll look at four key subgroups: amoeba, epicomplexa, sometimes called coccidia or Sporozoa flagellates, and ciliates. Then, moving to the multicellular metazoa, we have two main branches here. First, the helminths, the worms. These split into nemathelminthes, those are the roundworms, and platyhelminthes, the flatworms. And the flatworms themselves divide into trematodes, the flukes, and cestodes, tapeworms. Lots of worms.
Definitely sounds like it.
The other big branch of metazoa is the arthropods. This includes things like insecta, insects, arachnida, spiders, mites, ticks, crustacea, like crabs and copepods, and myriapoda, centipedes, millipedes. And one other crucial distinction, functionally speaking, is where they live. Endoparasites cause infections inside the host body. Ectoparasites cause infestations on the outside surface.
Perfect. Let's really zoom in on the protozoa now, these single-celled guys. What exactly are they, and what are their kind of defining biological features that make them so good at being parasites?
Protozoa are really fascinating. They're single-celled, microscopic eukaryotes, and almost all of them are motile. They can move. They live in incredibly diverse places, including inside us. Biologically, they're heterotrophic. They can't make their own food. They have to ingest nutrients, often engulfing particles into little food vacuoles. That's key to their parasitic lifestyle.
Makes sense.
Feature-wise, they have a plasma membrane controlling what goes in and out, usually a single nucleus, though some, like ciliates, have two, which is pretty unusual. Their cytoplasm is often divided into an outer, clearer ectoplasm used for moving or protection, and an inner granular endoplasm, where all the metabolic action happens, full of organelles. And of course, there are specialized bits for moving: pseudopodia, flagella, or cilia.
That's a great picture of their insides. So it sounds like how they move is a really big part of their identity.
Yeah.
Can we group them just based on that? And can you give us some key examples for each type of movement?
Absolutely. It's a very common way to group them. First up, the amoebae. They move using pseudopodia, or false feet. They basically extend bits of their cytoplasm and ooze along. The classic example you need to know is Entamoeba histolytica, the cause of amoebic dysentery.
Right, the oozing ones.
Then you have the ciliates. They're covered in rows of short, hair-like cilia that beat together, allowing for a quite rapid, coordinated movement. Balantidium coli is the main human pathogen here. Next are the flagellates. They use one or more long, whip-like flagella to propel themselves, sort of like swimming. Giardia lamblia, causing traveler's diarrhea, is a very common flagellate. And finally, perhaps the most intriguing for medicine, the apicomplexa, also known as sporozoa or coccidia. What's really interesting is they lacked specific locomotor organelles in their key stages. They're essentially non-motile, think Plasmodium species, the malaria parasites. They rely on host cells or fluids for movement. Their lack of independent movement means they've evolved incredible ways to invade and manipulate host cells.
Wow, no legs, no problem. So beyond movement, how else do we categorize protozoa, especially thinking about where they live in the host? Does that tell us something important?
Yes, definitely. Their address within the host is crucial for understanding the disease they cause. We group them by habitat. So luminal protozoa live in the hollow organs, Giardia in the small intestine, Entamoeba and Balantidium in the large intestine, Trichomonas vaginalis in the urogenital tract.
Okay, makes sense.
Then there are the blood protozoa. These include the hemoflagellates like trypanosoma, sleeping sickness, Chagas, and Leishmania, which circulate in the blood or lymph. And also the intra-erythrocytic sporozoa like Plasmodium, malaria, and Babesia, which actually live inside red blood cells.
Inside the cells.
Exactly. And finally, tissue protozoa. They set up shop in various body tissues. This includes tissue amoebae like Acanthamoeba and Naegleria fowleri, the brain-eating amoeba, and tissue sporozoa like Toxoplasma gondii. Knowing their preferred location helps predict symptoms and pathology.
That's a really helpful way to frame it, their location. Now, survival. What are the basic developmental stages protozoa go through, and what's the significance of each stage for, sticking around and spreading?
They typically have two main stages, which are key to their survival and transmission. First is the trophozoite. Think of this as the active, growing, feeding, and multiplying stage. It's the form that's metabolically active inside the host, often causing the disease symptoms.
The active.
Right. The second stage is the cyst. This is the dormant, resting, and highly resistant stage. It's often the infective form. Cysts form when conditions get tough, like outside the host or passing through the stomach. This process is called encystment. The cyst wall protects the parasite. It's like a little survival pod. When it reaches a favorable environment in a new host, it undergoes excistation, turning back into a trophozoite to start the infection. This cyst stage is absolutely crucial for transmission for many protozoa.
That's a clever strategy. Okay, this is really key for the students listening. Which protozoa are the most important medically, the must-knows? And where do they fit in these groups we've discussed?
Excellent question. For the apicomplexa coccidia, top of the list is Plasmodium species, P. falciparum, P. vivax, P. malariae, P. knowlesi, P. ovale, all causing malaria. Also crucial are Toxoplasma gondii and Cryptosporidium and Isospora.
Okay, malaria parasites, Toxoplasma crypto.
Exactly. For the amoebae, Entamoeba histolytica is the big one for amoebiasis. And don't forget the free-living amoebas, the FLAs like Naegleria fowleri and Acanthamoeba species. Rare, but deadly.
All right, the FLAs.
In the flagellates, you absolutely need to know Giardia lamblia, Trichomonas vaginalis, the Trypanosoma species, T. cruzi for Chagas, T. bruchei for sleeping sickness, and Leishmania species.
Got it. Giardia, Trichomonas, Trypanosoma, Leishmania.
And finally, for the ciliates, the main one is Balantidium coli. Memorizing these key players and their groups is essential.
Definitely a critical list.
Yeah.
Now, how do these tiny things reproduce? Is it all the same, or do they have different strategies?
They actually use both asexual and sexual reproduction, sometimes both within the same complex life cycle. It gives them flexibility. Under asexual reproduction, there are a few main types. Binary fission is the simplest. One cell just divides into two identical daughters. Entamoeba does this. Great for rapidly increasing numbers.
This is bull split.
Yep. Then there's multiple fission, or schizogony. This is more dramatic. The nucleus divides many, many times before the cell itself divides. So one parent cell releases a whole burst of daughter cells called merozoates all at once. Plasmodium does this inside red blood cells and liver cells. It leads to that exponential growth that causes malaria symptoms.
An explosion of parasites.
Pretty much. And there's also budding, sometimes called endodiogeny, where daughter cells form either on the surface or inside the parent cell. Toxoplasma uses this. It's perhaps useful for maintaining chronic low-level infections.
Interesting. What about sexual reproduction?
Sexual reproduction is also vital, especially for genetic diversity and transmission. We see syngamy, which is basically the fusion of two gametes, like sperm and egg, but simpler, to form a zygote. Plasmodium does this in the mosquito gut. It's essential for forming the oocyst, which then produces the sporozoites that infect humans.
So sex in the mosquito.
You got it. And then there's conjugation, which is a bit different. Two cells temporarily join up, exchange some genetic material specifically from their micronuclei, and then separate. Balantidium coli does this. It's not really making more parasites, but it shuffles the genetic deck, maintaining diversity.
Fascinating. Okay, from making more of themselves to their actual journeys, what are the general life cycle patterns for protozoa? How simple or complex can these get?
There are two main patterns. A direct life cycle, which is simple. The parasite only needs one type of host to complete its whole cycle. Trichomonas vaginalis is a good example. It just goes from human to human.
One host, simple.
Exactly. Then you have the indirect life cycle, which is more complex. This requires more than one type of host. Malaria parasites are the classic example, needing both humans and mosquitoes. In these complex cycles, we talk about the definitive host. That's where the parasite reproduces sexually, often the human in many cases we study, and the intermediate host, which harbors the asexual or larval stages, like the mosquito for malaria. These indirect cycles often involve amazing adaptations for switching between hosts.
All right, let's totally shift gears now. We've covered the single-celled protozoa. Let's move on to the multicellular guys, the metazoa. What are the big groups here, and what really makes them different?
Right, the metazoa. The key difference, as we said, is they're multicellular. They have specialized cells forming tissues, sometimes complex organs. This allows for much larger sizes and more intricate body plans compared to protozoa. The two major groups of parasitic metazoa we focus on are helminths, the worms, and arthropods. And remember, the helminths break down into nemathelminthes, roundworms, and platyhelminthes, flatworms, with flatworms further dividing into trematodes, flukes, and cestodes, tapeworms. Arthropods are the insects, ticks, mites, etc.
Let's tackle the worms first. That seems like a huge, diverse group. Can you break down the nematodes, trematodes, and cestodes a bit more, maybe with common examples we'd see clinically?
Absolutely. Let's start with nematodes, the roundworms. They're cylindrical, unsegmented, very common, intestinal ones. Think Ascaris lumbricoides, the giant roundworm, yeah. Hookworms, which can cause anemia, and Enterobius vermicularis pinworm, super common in kids.
Okay, Ascaris, hookworm, pinworm.
Then tissue nematodes. Cutaneous larva migrans is one that's offered animal hookworm larvae migrating under the skin. And blood and tissue ones, the filarial worms, Wuchereria bancrofti and Brugia malae, causing lymphatic filariasis, elephantiasis, and Loa loa, the eye worm.
Right, so filarial worms.
Next, Cestodes tapeworms. These are flat, segmented, look like tape or ribbon, intestinal. Tadenia solium, pork tapeworm, and Tadenia saginata, beef tapeworm, are the big ones. Tissue. Echinococcus granulosus causes hydated cysts in organs like the liver or lungs.
Tapeworms, I got it.
Finally, trematodes, the flukes, generally flat, leaf-like, and unsegmented, although blood flukes are a bit more cylindrical. Intestinal, Fasciolopsis busci, liver flukes, Fasciola hepatica, Canorchis sinensis, lung fluke, Paragonomus westermanni, and blood flukes, The Schistosoma species Mansoni Hematobium japonicum causing schistosomiasis. It's quite a rogues gallery.
Oh, it really is. That's a lot of worms. So if you're trying to picture them, what are the absolute key features to tell them apart, like visually?
The body shape is probably the most immediate giveaway. Nematodes are cylindrical, like a piece of spaghetti, unsegmented.
Round.
Trematodes are usually flat and leaf-shaped, unsegmented. Think of a small leaf, maybe, except for the schistosomes, which are more slender.
Flat, leaf-like.
And cestodes are flat and tape-like, but the key is they are segmented. They have those repeating sections called proglottids, like a long ribbon made of little segments.
Like I meant to take. Okay.
Other quick differences. Size varies hugely, from tiny nematodes to massive tapeworms meters long. Sexes too, nematodes usually have separate males and females, dioecious. Cestodes are typically hermaphrodites, monoecious, having both sets of organs in each segment. Trematodes are mostly monoecious too, except for schistosomes, which are dioecious. Those are the big tells.
That helps clarify things. So like protozoa, these worms have life cycles too.
Mhm.
What are the general patterns for helminths? Are they mostly simple or complex?
They follow the same basic patterns, direct or indirect. A direct life cycle is simpler, needing only one host, usually humans. The infective eggs or larvae pass out of the host, maybe develop a bit in the environment, and then infect another human directly. Ascaries, hookworms, pinworms often have direct cycles.
One host.
Right, but many helminths have indirect life cycles, needing multiple hosts. You have the definitive host, where the adult worm lives and reproduces sexually, often us, and one or more intermediate hosts, where larval stages develop. Think of schistosoma needing snails, Taenia needing pigs or cattle, the filarial worms needing mosquitoes or black flies. These complex cycles often involve intricate adaptations and are key targets for control measures. Breaking this cycle at the intermediate host stage is a common strategy.
That makes perfect sense from a public health view. Okay, finally, let's touch on arthropods. We know many are vectors, but some are parasites themselves. What are the main classes and what defines them?
Arthropods are a massive group invertebrates with that hard exoskeleton and jointed legs. Hugely important in parasitology. The main classes to know: insects, 6 legs, 3 body parts, head, thorax, abdomen, usually antenna and often wings. Mosquitoes, fleas, lice, flies are key examples, acting as vectors or ectoparasites.
6 legs, 3 parts.
Arachnids, 8 legs, 2 body parts, cephalothorax, abdomen, no antenna, no wings. Spiders and scorpions fit here, but medically we focus on ticks and mites, like scabies mites, which are in the Acarina subgroup. They often have a more fused, sac-like body.
8 legs, 2 parts, ticks and mites.
Crustaceans, usually 10 legs, 2 body parts, 2 pairs of antennae. Think crabs, shrimp. But tiny ones like cyclops or copepod are crucial intermediate hosts for some worms, like guinea worm or fish tapeworm.
Crustaceans like cyclops.
And myriapods, many legs, segmented body, centipedes, millipedes. Less directly involved as common parasites or major vectors of human disease compared to the others, but still part of the phylum.
Okay. And arthropods are famous for changing shape as they grow, right? Can you explain the main types of metamorphosis?
Yes, metamorphosis is key to their development. 2 main types: holometabolous or complete metamorphosis. This has 4 distinct stages: egg, larva, pupa, and adult. Think butterflies, but also mosquitoes and flies. The larva, like a maggot or caterpillar, looks totally different from the adult and often lives differently. The pupa is a resting transitional stage.
Egg, larva, pupa, adult. Complete change.
Exactly. Then there's hemimetabolous, or incomplete metamorphosis. This has 3 stages: egg, nymph, and adult. Things like lice, bugs, grasshoppers do this. The nymph looks like a miniature version of the adult, just without fully developed wings or reproductive organs. It just molts and gets bigger until it reaches the adult stage.
Egg, nymph, adult. Like a mini-me growing up.
Precisely. Understanding whether an insect vector has complete or incomplete metamorphosis is really important for control, because you might need to target different stages, like larvae in water from mosquitoes or nymphs in adults living on the host for lice. So today, we've really journeyed through the parasite world, haven't we? From those single-celled protozoa, looking at how they move and live, to multicellular worms, roundworms, flatworms, tapeworms, and finally the arthropods. Understanding their forms and life cycles, it's a huge field. But hopefully this gives you a solid framework.
Thank you to Dr. Mohammed Wiesman for providing the notes. Thank you so much for joining us on this deep dive. Don't forget to like, comment, share, and subscribe. It really helps others find this session. Keep learning parasitology the fun way, and we'll definitely meet again in another session. Bye for now.